Benjamin Franklin's 300th anniversary marks a significant milestone to reflect on his contributions. Franklin played a pivotal role in shaping the United States of America, and his groundbreaking work in electricity earned him the title of first American electrician. In 1751, Franklin published his work, Experiments and Observations on Electricity. This publication came decades before Michael Faraday's discoveries. To commemorate Franklin's legacy, acquiring and reading Experiments and Observations on Electricity is essential, as this seminal work provides a glimpse into Franklin's scientific experiments and insights. Reflecting on his achievements is another step in remembering Franklin's impact on the fields of science, politics, and American history. Inspire future generations by sharing Franklin's story with children and young people, instilling in them a love of science and a passion for pursuing knowledge. By recognizing and celebrating Benjamin Franklin on his 300th birthday, we pay tribute to an American icon who continues to inspire and educate us today. Let us ensure that his legacy lives on for generations to come. Franklin's experiments involved grounding, conduction, and the behavior of charged objects. He delved into the nature of positive and negative charges, understanding how they interact and neutralize each other. His famous kite experiment, though debated in its exact details, demonstrated the electrical nature of lightning, linking atmospheric phenomena to static electricity. It is important to note the dangers of replicating this experiment. Franklin also invented the lightning rod, a crucial safety device that protects buildings from lightning strikes by providing a safe path for electrical discharge to the ground. This invention stemmed directly from his research on electricity and his understanding of how to attract and conduct electrical charges. Franklin's work laid the foundation for many later electrical discoveries and technologies. His observations and terminology, such as positive and negative charges, are still used today. Franklin's scientific inquiry extended beyond electricity. He made observations and contributions to fields such as meteorology, oceanography, and medicine. He studied weather patterns, the Gulf Stream, and developed bifocal lenses. His scientific curiosity and commitment to experimentation made him a polymath whose work had a lasting impact across multiple disciplines. Understanding the concepts presented in Experiments and Observations on Electricity requires a grasp of basic electrical principles. Firstly, electric charge is a fundamental property of matter that can be either positive or negative. Like charges repel each other, while opposite charges attract. Secondly, electric current is the flow of electric charge, typically electrons, through a conductor. Current is measured in amps. Thirdly, voltage, also known as electric potential difference, is the force that drives electric current through a circuit. It is measured in volts. Fourthly, resistance is the opposition to the flow of electric current. It is measured in ohms. Ohm's law describes the relationship between voltage, current, and resistance. Voltage equals current times resistance, or volts equals amps times ohms. A circuit is a closed loop that allows electric current to flow from a power source through various components and back to the source. Circuits can be series, where components are connected in a single path, or parallel, where components are connected in multiple paths. Series circuits have the same current flowing through all components, while parallel circuits have the same voltage across all components. Electrical power is the rate at which electrical energy is transferred. It is calculated as power equals voltage times current, or power equals volts times amps, and is measured in watts. Energy is the capacity to do work and is measured in joules or kilowatt hours. Electrical safety is crucial when working with electricity. Insulation is used to prevent electric shock by providing a non-conductive barrier around wires and components. Grounding provides a safe path for fault current to flow, preventing electrical hazards. Circuit breakers and fuses are overcurrent protection devices that interrupt the flow of current when it exceeds a safe level, preventing damage to equipment and reducing the risk of fire. Capacitors store electrical energy in an electric field. They consist of two conductive plates separated by an insulator. Capacitance is the measure of a capacitor's ability to store charge and is measured in farads. Inductors store energy in a magnetic field. They consist of a coil of wire. Inductance is the measure of an inductor's ability to store energy and is measured in henries. Diodes are semiconductor devices that allow current to flow in only one direction. They are used in rectifiers, which convert alternating current AC to direct current DC. Transistors are semiconductor devices that can amplify or switch electronic signals. They are used in a wide range of electronic circuits, including amplifiers, oscillators, and switches. Integrated circuits, ICs, are complex electronic circuits that are fabricated on a single semiconductor chip. They can contain millions or even billions of transistors and other components. Digital circuits operate on discrete levels of voltage, typically representing binary values of 0 and 1. They are used in computers, microprocessors, and other digital devices. Analog circuits operate on continuous ranges of voltage and current. They are used in amplifiers, filters, and other analog devices. Electromagnetic induction is the process by which a changing magnetic field induces a voltage in a conductor. This principle is used in generators and transformers. Generators convert mechanical energy into electrical energy by rotating a coil of wire in a magnetic field. Transformers change the voltage of an alternating current signal. They consist of 2 or more coils of wire wound around a common core. Electrical standards and codes such as the National Electrical Code (NEC) provide guidelines for the safe installation and operation of electrical systems. These standards are developed by organizations such as the National Fire Protection Association (NFPA) and Underwriters Laboratories (UL). Understanding electrical concepts is essential for anyone working with electrical systems or devices. By mastering these principles, one can design, build, and maintain safe and efficient electrical systems. Electrical engineering is a field that deals with the design, development, and testing of electrical equipment and systems. The electrical engineers work in a wide range of industries, including power generation, telecommunications, electronics, and aerospace. The field is constantly evolving, with new technologies and applications emerging all the time. Benjamin Franklin's early work helped lay the groundwork for this technological advancement. The development of electrical power systems has revolutionized modern society. Electrical power is used to light our homes, power our appliances, and run our industries. Power plants generate electricity using various sources of energy, including fossil fuels, nuclear power, and renewable energy sources such as solar, wind, and hydro. The electricity is then transmitted over long distances through high-voltage transmission lines to substations, where the voltage is reduced for distribution to homes and businesses. Electrical safety is a critical concern in the design and operation of electrical power systems. Protective devices, such as circuit breakers and fuses, are used to prevent overloads and short circuits, which can cause fires and electrical shocks. Grounding systems are used to provide a safe path for fault current to flow, minimizing the risk of electric shock. Understanding electrical circuits is essential for anyone working with electrical systems. A circuit is a closed loop that allows electric current to flow from a power source through various components and back to the source. Circuits can be series, where components are connected in a single path, or parallel, where components are connected in multiple paths. The behavior of a circuit depends on the components that are connected in the circuit, such as resistors, capacitors, and inductors. Resistors impede the flow of electric current and are used to control the current and voltage in a circuit. Capacitors store electrical energy in an electric field and are used to filter signals and store energy. Inductors store energy in a magnetic field and are used in filters and resonant circuits. Electronic devices rely on the manipulation of electrical signals to perform various functions. These devices range from simple diodes and transistors to complex integrated circuits that contain millions or even billions of components. Diodes allow currents to flow in only one direction and are used in rectifiers and signal detectors. Transistors can amplify or switch electronic signals and are used in a wide range of electronic circuits. Integrated circuits (ICs) are complex electronic circuits that are fabricated on a single semiconductor chip. They can contain millions or even billions of transistors and other components. Digital electronics deals with circuits that operate on discrete levels of voltage, typically representing binary values of 0 and 1. Digital circuits are used in computers, microprocessors, and other digital devices. Analog electronics deals with circuits that operate on continuous ranges of voltage and current. Analog circuits are used in amplifiers, filters, and other analog devices. The field of electromagnetics deals with the interaction between electric and magnetic fields. Electromagnetic waves such as radio waves, microwaves, and light waves are used to transmit information over long distances. Antennas are used to transmit and receive electromagnetic waves. Motors convert electrical energy into mechanical energy and are used in a wide range of applications from electric vehicles to industrial machinery. Generators convert mechanical energy into electrical energy and are used in power plants. Control systems are used to regulate and control the behavior of electrical and mechanical systems. These systems use feedback to maintain a desired output, even in the presence of disturbances. Instrumentation and measurement are essential for monitoring and controlling electrical systems. Instruments are used to measure voltage, current, power, and other electrical quantities. These measurements are used to ensure that the system is operating correctly and to identify potential problems. Signal processing is used to extract information from electrical signals. This includes filtering, amplification, and modulation. Communication systems use electrical signals to transmit information over long distances. These systems include telephones, radios, and the Internet. Computer networks use electrical signals to transmit data between computers. These networks can be wired or wireless. Renewable energy sources such as solar, wind, and hydro are becoming increasingly important as the world seeks to reduce its reliance on fossil fuels. Solar panels convert sunlight into electricity. Wind turbines convert wind energy into electricity. Hydroelectric dams convert the energy of flowing water into electricity. Energy storage systems are used to store electrical energy for later use. Batteries are the most common type of energy storage system. Supercapacitors and flywheels are also used for energy storage. Electric vehicles are becoming increasingly popular as concerns about air pollution and climate change grow. Electric vehicles use electric motors to propel the vehicle. They are powered by batteries that can be recharged from the electric grid. Smart grids are electrical grids that use digital technology to improve the efficiency, reliability, and security of the grid. Smart grids can monitor and control the flow of electricity in real time, allowing for more efficient use of resources. The future of electricity will be shaped by technological advancement and societal needs. Renewable energy, energy storage, and smart grids will play an increasingly important role in the electrical power system. Electrical engineers will continue to develop new technologies to meet the challenges of the future.